Okay, so today I'm going to go through Chapter 6, which is Cramer's rule and matrix operations. I have opened my version of the course notes, but I'm going to go through things by hand here and explain along the way some of the things that we come across in the course notes. So let's have a look at our first example here. So Cramer's rule gives formulas for solving systems of linear equations. For example, the following system, minus 2x minus 5y is minus 14, and minus 2x, oh hang on, that's plus over there, plus 4y is 11. So these two equations, solved as a linear system, can be done simply by adding the two equations, but let's also visualize these, because this first equation can be written by taking the y over to the one side. We can write this 5y is equal to 2x plus 14, and so dividing by 5 would give us y equal to 2/5 x plus 14 over 5. So here I have a slope and a y-intercept. This equation here gives me, okay, again we can take the 2x over to the right hand side and then divide by 4. So that would give, let's see, 2x over 4 was 1/2 x, and then plus 11 over 4. So here's my slope, here's my y-intercept. So you see straight away that these do not have the same slope, and therefore they're not parallel, so they must intersect. Alright, now that point of intersection there is the solution to the simultaneous system. So these two equations intersect because they don't have the same slope, and we can find this intersection algebraically. There's a saying that goes, think geometrically and prove algebraically. It's a very useful one. Now one way to solve this system right here would be to add the two equations. So if I add the two equations, then the x's will vanish and I'll have an equation with only y in it. So we would get then minus 5y plus 4y is equal to minus 14 plus 11. And that says, once we simplify, it says minus y is equal to 11 minus 14 is minus 3. And so then multiplying both sides by minus 1 gives y is equal to 3. Okay, so we've got one of those. Now for the other one we can just back substitute, but we can actually just use this form and then solve for x, right? But actually let's sub in here. So 2x minus 5 times 3 equals minus 14. Okay, so that's minus 15 right there. We can add that to both sides, and so we would get 2x is 15 minus 14, which is 1, and so dividing by 2 gives x is 1/2. So this point of intersection here is 1/2, comma 3, right? But x is 1/2 and y is 3 as a solution to the simultaneous system. So that's one way to do it, right? And so I would call this elimination. However, you can also do this via substitution. So if we were to do this via substitution, and I'll just create a little box here to do this via substitution, because you see what we've already done is we've solved for y, so it's quite simple to substitute this value of y into the second equation. And so via substitution, minus 2x plus 4 times 2/5 x plus 14/5 equals 11. And then we proceed to solve for x. So to do that with this, we would need to expand this part right here. And so we have minus 2x plus 8 over 5x plus, let's see, 4 times 14 is 56. So 56 over 5 equals 11. Okay, so it looks like the fractions are a little bit more painful to deal with here, but you should get the same result. So anyway, carrying on with this, slide the paper down a little bit. So we want to add the two of these, but we need a common denominator of 5. So we'll view that as 8 minus 10 all over 5 times x. And then this will take over to the right-hand side. So 11 is 55 over 5. So 55 minus 56 all over 5. Now we can multiply both sides of the equation by 5 to make the 5's vanish, which would probably be a good idea. So then if we do that, we've got minus 2x equals minus 1, and again you have x is 1/2. Okay, and then you would take this and substitute back into your equation to get y equals 3. Okay, so both methods are fine. This method we call elimination because we eliminated x by adding the two equations. Normally though, it's not that easy. You would have to multiply one equation by something and another equation by something else in order so that the addition of the two equations makes one of the letters vanish. Alright, now this is probably the preferred method, even though you might find it conceptually a little bit more difficult. And the reason I would say it's the preferred method at this point is because we're going to move on to talk about Gaussian elimination. And Gaussian elimination exactly does this process, but it does not represent the letters x and y in that process. We do so with matrices, but it's the very same process of elimination. It's just a little bit more sophisticated. Okay, so I'm going to move on and look at the next page of my notes and talk to you about what I see there. Alright, so the next one is an example, and it says use substitution to solve the system. Oh, didn't we just do that? Yeah, that's the same one. So I've done that in two ways. Okay, so I'll move on. So our next topic is solving the same system using Cramer's rule. So Cramer's rule requires us to introduce matrices. So the first thing I'm going to do is just rewrite this system of equations. Okay, so we've got 2x minus 5y is minus 14, and minus 2x plus 4y is 11. So what we want to do first is write this as one matrix equation. Now I'm just going to take the numbers. Here we have these in alphabetical order, x followed by y, left to right when we write it down. So I'm going to write down a matrix from those coefficients, or the numbers next to the letters. So A equals the matrix 2, minus 5, minus 2, and 4. And then I'll introduce another matrix that is a column from the right hand side. Okay, but I see my notes have C, so I'll write C instead of B. So minus 14, 11. Okay, and if we introduce another matrix uppercase X as X, Y, then this equation right here, written as a matrix equation, is the equation 2 minus 5 minus 2, 4, multiplied by the matrix xy equal to minus 14, 11. Now the focus there will take a little while. Yeah, there we go. Okay, so this is the corresponding matrix equation to this pair of scalar equations. And to fully understand that, you'll need to read ahead a little bit on matrix multiplication, because if we multiply this out on the left, basically I take this row and pair it with this column, multiply 2 times x and minus 5 times y, and take the sum, just like you would in a dot product. So multiplying that out, we have 2x minus 5y in our first row of the product matrix, and then minus 2x plus 4y equal to minus 14, 11. And so you can see when we match the entries in each of these matrices, we get each of these equations. So this matrix equation agrees with this pair of scalar equations. Now we can write this as one single matrix equation because we've already set out these letters, and that says AX equals C. Okay, so we're introducing Cramer's method here for solving this system. It's a matrix method, but it requires that we take determinants of certain matrices that we have not yet defined. So we'll define those now. So define A subscript x to be equal to, now I can see in my notes the right hand, that should say B there, B concatenated with A2. So I'll write C instead, because we're using the letter C here. So C concatenated with A2. Now A2 is just the second column, so I'll write up here A equals A1 concatenated with A2. That just means glue the two columns together to form this matrix. Okay, so in this case, and I need to scoot the paper over. Right, so in this case, C is the right-hand side of the matrix equation there. So this is AX equal to minus 14 above 11, and then next to that we put the second column of the matrix A, and we have minus 5, 4. So this is our matrix A subscript X. Okay, so in the same way we can form a matrix A subscript Y. So A subscript Y is equal to the concatenation of A1 with C. Alright, so A1 with C means just take the first column of A and then put the column of C in the second column of the resulting matrix. So in this case we would have 2 over minus 2 and then minus 14, 11. So these are the two matrices that we need to use Cramer's rule. Alright, but remember it's a rule about determinants, so we also need the determinant of the matrix A itself. I'll rotate this a little bit so the light hits the page better. Okay, so we also need the determinant of the matrix A. Here's the matrix A. So det of A, so sometimes I write out the word det, but it's the same as just putting vertical lines around your entries. So 2 minus 5 minus 2, 4. So remember this is 2 times 4, so 2 times 4 is 8, and then subtract the product of these two. But the product of those two is positive 10, so we're subtracting 10. And so the determinant of A is 2. Alright, now Cramer's rule would say that x is equal to the determinant of ax over the determinant of a and so we need the determinant of this matrix as well, but let's do that just looking at this, and then we'll write it here. So 4 times minus 14 is minus 56, and then we're subtracting minus 55, so that's plus 55. Okay, now determinant of a, we already calculated that as 2, and so we have the difference, minus 56 and plus 55 is minus 1, so minus 1/2. Okay, now similarly we can calculate y to be equal to det of ay over the determinant of a So the determinant of this matrix here is 22 minus the product of these two is 28. So 22 minus 28 all over 2. And so that gives us, let's see, minus 6 in the numerator, so minus 3. Alright, now I'm wondering, something seems a little bit suspicious. So it would seem that I've got the wrong determinant for a itself. It should actually be the negative of that. So let's have another look at this. So the determinant of a is 8 minus 10. Okay, that's minus 2. Alright, so this should be minus 2, which would change this to plus. This is minus 2, which changes this to plus. Okay, so again, via Cramer's rule, we get the point of intersection of the two lines being 1/2, comma 3. Okay, let's move on to the next page. Alright, so I'm up to remark 6.1. So if we have ax plus by equal to e and cx plus dy equal to f, so we have two lines. Let's suppose that x and y are the variables. Now we could have these lines intersecting, or they could be parallel, right? So if the determinant of the matrix A, B, C, D, which incidentally is AD minus BC, so if this is not equal to 0, then the lines intersect, and we have a unique solution. To the system that is this. Okay? And conversely, if you have a unique solution to the system, then you must have the determinant of the matrix A, B, C, D non-zero. Alright, so just notice from Cramer's rule, remember you had x equal to the determinant of ax over the determinant of a. Right, now imagine if this denominator were 0, then you could not get a number here for x, right? So you would not get a solution. So this agrees with Cramer's rule. Okay, so the next case is we could have parallel lines. So if the determinant of A, B, C, D is equal to 0, then the lines are parallel, and furthermore they could be the same line, right? So if you get a 0 determinant, then you know that your lines are parallel, but the lines being the same is a sub-case of parallel. So there's either no solution to the system, meaning that another word for that is inconsistent. So here I've just sketched two parallel lines, right? So there is no intersection with parallel lines. So this is no solution. Geometrically viewed, it's parallel lines. But the other case is when the lines coincide, and they are also parallel in that case, right? They just happen to be the same line. You have infinitely many solutions when the lines coincide. In fact, every point on the line is a solution to the system. Okay, let's have a look at example 6.3, which asks us whether a particular system has a unique solution, no solution, or infinitely many solutions. So our system is x plus y equal to 1 and x minus y equal to 3. Okay, so let's have a look at the corresponding matrix equation. So this would be 1, 1, 1 minus 1 multiplied by xy equals 1, 3. And so the matrix, so this is A, this is X, and this is C. Okay, so we ask, is the determinant of the matrix A equal to 0? So det of 1, 1, 1 minus 1 is equal to the product of the diagonal elements, minus 1, subtract the product of the off-diagonal elements. So minus 1 is minus 2, and minus 2 is non-zero. So we see that there is a unique solution. So hence, system has a unique solution. So now let's find it, because it's easy enough to find. So if we were to add the two equations, then the y would vanish, and we get 2x equal to 1 plus 3 is 4. And so dividing by 2, you get x is 2. Now substituting that back into, say, the second equation, you have 2 minus y equals 3. And so y is equal to, taking that over to the right, taking the 3 over to the left, 2 minus 3, which is minus 1. Okay, now we could check, right? Because 2 plus minus 1 equals 2 minus 1 is 1. So this agrees with the first equation. So we have a point of intersection of the lines, which is the point 2 minus 1. Okay, so it has a unique solution, and yes, we're easily able to find it. Okay, let's have a look at our next example. Does the system x plus y equal 1 and x plus y equals 6 have a unique solution, no solution, infinitely many solutions? Okay, so let's look at the determinant. So A equals the matrix 1, 1, 1, 1. Let's take the determinant of that matrix. So 1 times 1 is 1, minus 1 times 1, 1, and we get 0. So in this case, we see that the lines must be parallel, and they could be the same line. However, if you try to solve this system by, say, subtracting the first equation from the second equation, so subtracting second equation minus first equation, you get 0 on the left is 6 minus 1. And obviously that's bogus, right? Because 0 is not equal to 5. So this gives a contradiction. So a contradiction to the assumption that there was a solution. So really up here you said assume there is a solution. Okay, so if there is a solution, then you could do subtraction of the two equations, and you would get this, which is a contradiction, because 0 is not equal to 5. Okay, so we get a contradiction to the assumption that there's a solution, so we conclude that the assumption was false, so hence no solution. And so geometrically what that looks like is parallel lines. Alright, let's have a look at another example. Okay, and then further commentary on that. So if you did this via Cramer's rule, you would have a 0 determinant for A, and so x equals det of A subscript x over det A gives you something over 0, right, which is not a number. So straight away from the calculations, via Cramer's method, you would know that there's no solution. Or there are infinitely many solutions. You have to do a little bit more investigation if you get a 0 determinant. Okay, next example. Does the system x plus y equal 1 and 3x plus 3y equal 3, does this have a unique solution? No solution or infinitely many solutions. Okay, so again we write down a matrix corresponding to those coefficients. A equals 1, 1, 3, 3, and then take the determinant of that matrix. We get 3 minus 3, which is 0. Okay, so we know we've got one of two cases. We've got either no solutions or infinitely many solutions, right? So are they two distinct parallel lines, or do those parallel lines coincide? So let's have a closer look then. Now if we multiply the first equation by 3, we would see that we get the second equation. So 3x, anyway, multiplication of equation 1, labeling this equation 1 and equation 2, by 3, we have 3x plus 3y equals 3, which is equation 2. So we see that the equations coincide, right? And so subtraction would give you 0 equals 0. That's not a contradiction. So you just see then that the equations coincide, right? This equation is a multiple of this one, and vice versa. This is a multiple of this one. So the answer to this question is answer number C, infinitely many solutions. So if there are infinitely many, let's find one. So what I can do is take this equation and I'll write x equals x, and then y equals, let's see, if we rearrange it, we have 1 minus x. So let's now form a point. The point xy on the line can be rewritten in terms of one letter x, just like this. And then I can choose x, right? I can choose x as any real number. So we'll say where x is any real number. And this point is on the line y plus x equals 1. So this is how we get an infinite number of solutions. Okay, so e.g., for example, if x is equal to 86, then the point 86, 1 minus 86 is minus 85, is on the line x plus y equals 1. All right, let's move on. Okay, now if you were to use Cramer's rule on this system, you get a zero determinant for a, and so that would give you a zero denominator, right, which gives you, well, not a number, right, so you have to do further investigation at that point. All right, moving on to example 6.6. So in 6.6, we've got a 3 by 3 system. X plus 3y plus 2z equals 5, minus 2x minus 5y minus z equals minus 1, 2x plus 4y equals minus 2. And so the question says, determine whether the system has a unique solution, and if so, use Cramer's rule to solve it. Alright, so I can see the focus needs to get fixed. Hopefully that'll fix itself up in time. There we go. Alright, so let's write out first the matrix A. So A equals, I'm just reading off the coefficients, 1, 3, 2, minus 2, minus 5, minus 1, and then 2, 4, and 0. Okay, C is the matrix. That's a column, 5 minus 1 minus 2. X is x, y, z. And so our matrix equation is AX equals C. But then we need to form the three matrices A subscript X. So what we're doing to form this is we are replacing the X column of the matrix A with C. Right, so it's C concatenated with A2 and A3. So C, A2, A3, which is the column 5 minus 1 minus 2, followed by the second column of A, so 3 minus 5, 4, and then 2 minus 1, 0. So that's AX, and then you form AY in the same way. So AY is equal to A1 concatenated with C concatenated with A3. And so this is 1 minus 2, 2 in the first column, C in the second column, and A3 in the third column, so 2 minus 1, 0. Okay, AZ equals A1 concatenated with A2 concatenated with C. And so this is the matrix 1 minus 2, 2, 3 minus 5, 4, and then we put C here, so 5 minus 1 minus 2. Okay, now Cramer's rule requires us to calculate the determinant of this matrix because it goes in all of the denominators. So the determinant of A, and I think I should pull up some more paper here. Maybe there's a little space here. Okay, so the determinant of A equals, remember 1 times this determinant right here, obtained by crossing out the column and the row that 1 is in. So minus 5 minus 1, 4, 0, multiplied by 1, and then we subtract minus 2 minus 1, 2, 0, multiplied by 3, and then we add determinant minus 2 minus 5, 2, 4, multiplied by 2, Okay, we need to simplify this, so the product of those two is 0. So 0 minus minus 4 outside of 1. Subtract. Okay, minus 2 times 0 is 0. Minus minus 2 outside of 3. And then this one plus minus 8 minus minus 10 all times 2 and then we simplify this arithmetic. So here we've got 4 times 1 is 4, then minus, now that's plus 2 in there, so plus 2 times 3 is 6, so minus 6. Here we have minus 8 plus 10 is 2, so 2 times 2 is 4. So that is 8 minus 6 is 2. Okay, so det A is 2. Alright, now we have got to take the determinants of each of these. So I'll have to be a little bit careful here so we can see those plus see the working below. Alright, so the determinant det of AX equals, okay, so we have determinant of minus 5 minus 1 40 times 5 and then subtract determinant of minus 1 minus 1 minus 2 0 times 3 and then plus determinant minus 1 minus 1, sorry, minus 1 minus 5, isn't it? Minus 2 and 4 multiplied by 2. Okay, we need to simplify this. So the product of those is 0. Minus minus 4 is plus 4, so that's 4 times 5 is 20. And then subtract in brackets something times 3, so 0 minus 2, but then we have a minus out here, so I'll put minus 6 inside because minus 2 times 3 is minus 6. Okay, moving on to this, minus 4, so plus minus 4 minus 10 all outside of 2. So we've got 20 plus 6. Now this is minus 28. Okay, I'm going to check my notes to see if I'm on track. Looks okay. So 26 minus 28 is minus 2. Okay, so we do need the other two determinants, but let's go straight away to work out what x is. So x is equal to det of a subscript x over det of a. Now we already have det of a is equal to 2. So this is minus 2 over 2, which gives us minus 1 for x. Okay, so next, moving on to the determinant of a subscript y. Probably done a lot already, right? So maybe that's enough practice, but I'll do one more, just so we be sure we've covered it. Okay, so determinant of a subscript y is equal to det of 152 minus 2 minus 1 minus 1, 2 minus 2, 0. Okay, good. So this is determinant minus 1 minus 1 minus 2, 0 times 1. And then minus, so we do this number, cross out the column and the row that it's in, and form the 2 by 2 determinant that remains, minus 2 minus 1, 2, 0 multiplied by 5, and then plus 2 by 2 determinant times 2. But what we have remaining when we cross out the column and the row that the 2 is in is minus 2 minus 1 2 minus 2. Alright, so we need to simplify this. So we have in brackets something times 1 minus something in brackets times 5 plus something in brackets times 2. And so the product of minus 1 and 0 is 0. The product of minus 2 and minus 1 is plus 2, so we're subtracting plus 2. Okay, moving on to this, we've got 0 minus minus 2 is plus 2. Over here we've got 4 minus minus 2 is plus 2. So this is minus 2 for this one, minus 10 for this one, and 6 times 2 is 12, so plus 12 for this one. Okay, so this adds up to 0. So the determinant of a subscript y is 0. So Cramer's rule gives us that y equals det of ay over det of a. And so this is 0 over 2, which is 0. Okay, so far we've got x is equal to minus 1 and y is equal to 0. So if we just go back and look at the system, we can easily back substitute and find out what z has to be. Alright, so just taking the second equation. The second equation is minus 2x minus 5y minus z is minus 1. So I can sub these in there and get z and save myself the calculation of that third determinant, the determinant of a subscript z, right? And that might be reasonable at this point. Okay, so let's go ahead and do that. So 2 times minus 1 is 2. 5 times 0 is 0, so minus 0 minus z equals minus 1. Okay, so taking the minus z over to the right hand side and the minus 1 to the left, we've got z is equal to 2 plus 1 is 3. And then you might want to check that that agrees with the first equation, x plus 3y plus 2z is 5. So minus x plus 0 plus 6, yes, that does give 5. So, right, we've solved the system, but alternatively you could have calculated det of a subscript z over det of a, and this would be equal to z, right? So that's an alternative way to do it. A little bit more work because you have to calculate a 3 by 3 determinant to do it. Okay, let's move on to the next topic. Oh, okay, I can see. You should have a look in the notes because the system, we do have a unique solution here, right? We've got x is minus 1, y is 0, and z is 3. So this gives us a point, minus 1, 0, 3. It's a point of the intersection of the three planes. And the three planes were the three equations with the x, y, and z in them. Okay, so those three linear equations intersect in this point, minus 1, 0, 3. So again, you can think geometrically and calculate that point of intersection algebraically. Alright, let's move on to the next example. Consider another 3 by 3 system, and the system is x plus y plus z equals 2, x minus z equals 1, and x plus y equals 1. And the question here is, does this system have a unique solution? And if so, use Cramer's rule to find it. Okay, so does it have a unique solution? Well, we want to work out what the determinant of the matrix A is. So let's go ahead and write A equals 1, 1, 1, 1, 0, minus 1. And I'm just reading off the coefficients. And 1, 1, 0. Okay, the right hand side, let's call that C. We have 2, 1, 1. So the matrix equation is AX equals C, where The matrix X is X, Y, Z. Alright, so we need the determinant of the matrix A. So det of A is equal to determinant of 1, 1, 1, 1, 0, minus 1, 1, 1, 0. We'll wait for the focus there. Anyway, it'll come back in a moment. Okay, so this determinant expanding across the top row, we have determinant of 0 minus 1, 1, 0 times 1, subtract, crossing out the column that that middle one is in and the row that the middle one is in, we have 1 minus 1, 1, 0, and then we have plus. We're crossing out the third column and the first row, so 1, 0, 1, 1 multiplied by 1. Let's simplify this. So we've got 0 times 0 is 0, minus minus 1 is plus 1. So 1 times 1 is 1. And then this was supposed to be times 1 there. Okay, minus bracket 0 minus minus 1 is plus 1 by 1. And then we have plus 1 times 1 is 1 minus 0 times 1. So what do we get here? 1 minus 1 plus 1 gives us 1. So the determinant of A is equal to 1. Okay, this is not equal to 0, right? So the system has a unique solution. Alright, and so the next part says find it, but I'm going to take a little bit of a digression here and say, well, you could also calculate this determinant by expanding across the first column, for example, or the second column, for example, and it's the same process. You just have to pay attention to this checker pattern of plus and minus signs when you do so. So if I were to expand across the second column, for example, I'd be taking these numbers, and sometimes it's more convenient to do that because you might have some zeros in there telling you that the result would be 0. So calculating the determinant in another way, we know we should get 1, right? Alright, so expanding across the second column, so column 2 in the calculation, so we have a determinant multiplied by 1, but notice the first sign is minus, so we would start off with a minus sign there, and then the next sign is plus in our checker pattern, a determinant times the second entry in that second column, so times 0, and then minus, according to the checker pattern there, a determinant times the last entry of that column, which is 1. Okay, now we apply our same trick. We cross out the row and the column that that first 1 is in, and we get 1, 1, minus 1, 1, 0. Okay, next, if we move on to the second entry in that first column, cross out the row, the column and the row that it's in, and we have 1, 1, 1, 0. Okay, finally, moving on to the next entry, the 1, we cross out the column and the row that it's in, and we have 1, 1, 1, minus 1. Okay, now we simplify this, and we've got minus in brackets, 0 minus minus 1 is plus 1 times 1, and then plus brackets something times 0, so that's 0 minus 1, and then minus 1 minus 1 times 1. So simplifying this This up here gives us minus 1. This right here gives us plus 0. This right here is minus 2. And then times minus 1 is plus 2. So 2 minus 1 is 1. Okay, so we've calculated the determinant by expanding across the second column. For example, just to show you that you could do this in another way if it were more convenient. Right, and sometimes you might have symbols in here and it's more convenient to go across a different column or a different row in your expansion of the determinant. Okay, so now the problem, remember, is to use Cramer's rule to find the solution. So what we need to do now is form another determinant. We need the determinant of a subscript x, a subscript y, and a subscript z. So we've got to form the matrix a subscript x first, and then take the determinant. So what we do is we replace the column that x is in. So in other words, the x's are here, right? So this is the x column, which is the first column. We've got to replace the column of this matrix with C. Okay, so we form the matrix A subscript x equal to C, followed by the rest of the matrix A. So 1, 1, 0, minus 1, 1, 0. And we need to take the determinant of this. So dat of AX is this determinant. Okay, let's expand across the top row. So we have 1, minus 1, 1, 0, and then plus determinant times 1. So we have 1, 0, 1, 1. Okay, let's simplify this. So 0 times 0 is 0, minus minus 1 is plus 1, plus 1 times 2 is 2. Moving on, 0, take minus 1 there, so that's plus 1. We've got minus 1 when we take the minus inside. Okay, then 1 times 1 is 1, so plus 1 minus 0, and then times 1, so plus 1. And so I get a determinant of 2 for the determinant of AX. Alright, similarly, we form the determinant of AY. So we've got to form the matrix AY. So AY equals first column of A followed by C, because that's the Y column. So 2, 1, 1. And then the third column of A. Okay, and so we take the determinant of this. So dat of AY is equal to, so 1 minus 1, 1, 0, multiplied by 1. Subtract something times 2. Now the matrix is 1, minus 1, 1, 0 there, and then plus determinant times 1. This 2 by 2 determinant is 1, 1, 1, 1. Okay, let's simplify. We've got 0 minus minus 1, so that's 1 times 1 is 1. Then minus 0 minus minus 1 is plus 1 by 2. And then plus 0, because this determinant right here is 0. Okay, simplifying this one, we've got 1 minus 2 is minus 1. So the determinant of A subscript Y is minus 1. Okay, so now what we can do is say, let's do some calculations here. X is det of AX, over det of A. But the determinant of A is 1. So X is equal to 2 over 1, which is 2. similarly, y is equal to the det of ay over det of a. So we've got minus 1 over the determinant of a. Remember, this was the determinant of a right here. So over 1, and we get minus 1. So x is 2, y is minus 1, and remember we can back substitute to get z here, or we can calculate the determinant of a subscript z, but I think I've done enough determinants, so I'll just use x plus y plus z equals 2 to get z. So z is equal to 2 minus x minus y, so that's 2 minus 2 minus minus 1 is plus 1, and so z is equal to 1. Okay, so that gives us a point of intersection of the three planes. At the point of intersection of the three planes is x, y, z is 2 minus 1, 1. So here's our point, 2 minus 1, 1. Is a point of intersection of these three planes right here. Okay, and since the determinant of a was non-zero, we knew in advance that there would be a unique solution to that system. And thinking geometrically, that's the point of intersection here, 2 minus 1, 1. All right, let's move on to the algebra of matrices. Okay, so now what we're going to do is talk a little bit more about matrix multiplication. Alright, so let's just briefly discuss the 2 by 3 matrix 3, 2, 0, 1, 4, 5. Now this is a 2 by 3 matrix. Right? In other words, it's got 2 rows and 3 columns. So you can see it's not a square matrix. Okay, and so I'll just remind you that you cannot take the determinant of this, because if you tried, it wouldn't work out, right? So the determinant is not defined for a non-square matrix. However, you can still multiply non-square matrices together. Okay, now one way to abbreviate the entries here is to say let A subscript ij be the entry in the matrix A in the ith row and the jth column. Okay, so one way to abbreviate the matrix A then would to be to put square brackets A ij, where this is a representative of all of the entries within it. And then you might even put saying that it's an m by n matrix, so in this case you'd put 2 by 3 there to talk about it. Okay, now so if you had a matrix, say a bigger one, this here would abbreviate the entire matrix A11, A12, etc. The next term would be A13 and so on, and then A1n. So the second row would be A21, A22, etc., A2n. And then we can put vertical dots, but the next row would be A31, A32, and so on. But the last entry in this, or the last entry in the first column would be AM1, and then the last entry in the second column is AM2, dot, dot, dot. The last entry is AMN. Okay, so we can put vertical dots here and diagonal dots to say that it keeps going in this pattern, right? So this is the abbreviated way to write this. Now you might be asking, why don't we instead use A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, and so on, right? Well, the reason why is because there are only 26 letters in the English alphabet, right? That's not enough to represent, say, a, let's see, 26, huh? Okay, so what if I had to represent a, I don't know, a 5 by 6 matrix? So 5 times 6 has 30 entries in it, right? So 30 is greater than 26. So you run out of letters after writing so many. So this is a way to write a generic matrix like A, B, C, D, but when you need a lot more entries than A, B, C, and D. If it's not just 2 by 2 or 3 by 3. If it's an M by N matrix, then you can characterize the entries in this way, right? So by the ith row and the jth column. Alright, so it's useful to write it this way when you need to take sums and products. For example, right, rather than write out all of this, if I wanted to write what the sum of A and B is, I could say, well, I can characterize A as Aij. It's an M by N matrix. And then I can characterize the matrix B by Bij. And if that is also an M by N matrix, then that sum is defined. And in fact, I would just add the corresponding entries in the same row and column. And so I could characterize the sum as Aij plus Bij, just like this, and say that that's also an M by N matrix. And similarly, you could do that for the difference of the two matrices. Okay, similarly, I can characterize scalar multiplication of a number, a scalar times a matrix, in the same way. So the scalar k times the matrix A is, now you could set it out like this, right? And so we would have a k in front and have to bring in the k to every entry. But you see it's k times the matrix square brackets Aij, M by N, and then you bring the k in, and you've got a characterization of every entry in the product as k times Aij, and again it's an M by N matrix. So this just gives you a nice way to summarize what's going on inside. Okay, so now let's have a look at example 6.8. I need to grab some more paper, give me a moment. Okay, in example 6.8 we've got A equal to 320,145 and B equals 104 minus 412. Now both have the same dimensions, so 2 rows and 3 columns. So both are 2 by 3 matrices. And so the sum and difference are defined. Okay, so A plus B, we just add up the entries that are in the same row and same column. So just setting this out, we've got 3 plus 1 for this one plus this one, and then next 2 plus 0 for this and this, and 0 plus 4 for the next entry. Okay, next these entries in the second row and the third column, so that's 1 plus minus 4. So next in the second row and second column we have 4 plus 1, and then finally 5 plus 2. Okay, but incidentally, just randomly, let's pick one. So the entries, so A 23 equals 5, and then B 23 is equal to 2. So the entry A23 plus B23 2, 3 of the sum is just 5 plus 2, which is 7. So in other words, I'm just describing what that is. Okay, let's continue this. So we've got 4, 2, 4, and then minus 3, 5, 7 is the sum of those two matrices. Okay, similarly, you can take the difference. Have a look at what it says in the course notes. The difference, you just subtract these entries from these, and you get 2, 2 minus 4 in the top row, and then 5, 3, 3 in the second row. Okay, let's go ahead and do scalar multiplication. So 2b, for example, is twice the matrix 104 minus 4, 1, 2. And we just bring the 2 inside. So 2 times 1 is 2. 0, 8 minus 8, 2, 4. And that's 2 times b. Alright, we can also do minus b. So minus b is the scalar multiple minus 1 times b. So we bring the minus 1 in, and we just have minus 1, 0, minus 4. Minus 1 times minus 4 is plus 4, then minus 1, then minus 2. And this is minus b. Okay, so in general, now you probably want to look at the course notes for this. In general, this abbreviated notation gives you a way to take the product of any matrix. Okay, and I feel like I should screen share, but I don't want to change the setup here. So I'll just ask you to look at your course notes where you see a generic matrix. So A multiplied by B equals, and in the characterized form we've got Aij, and it's m by n, and then here we've got Bij. Now suppose this is n by q. Now the product of these two is only defined when the number of columns of the matrix on the left matches the number of rows of the matrix on the right. Okay, so fully set out, this would be A11, A12, and so on, A1n. And then we have A21, A22, and so on, up to A2n. Then we'll put vertical dots, AM1, AM2, the last entry is AMN. Similarly, the matrix B, let's assume it's B11, B12, up to B1Q in the first row. Then the second row, B21, B22, up to B2Q, because that is Q columns there. Okay, vertical dots, diagonal dots, and the last row has B N1, Bn2, up to Bnq. Alright, so this number of entries in the first row corresponds to the number of entries in the first column. So when I match this to this, multiply and add together, I can do that because the number of entries will match. Okay, so this product is defined because the number of columns of A equals the number of rows of B. So in the product, we do exactly that, A11 times B11. Alright, so we're going to get something massive here, so you might want to look at what you have in the course notes. So the first one is A11 times B11 plus A12 times B21, and so on, and the last part of that sum is A1n times Bn1. Okay, so you can continue. Now, next you take this times the second column, and so when we do that, we've got A11 times B12 plus A12 times B22 plus and so on, and then our last term in that sum is A1n times B1q. But we're not done here, right? This is the second entry in the first row of the product. There's more. So again, we take the first row times the, say, the jth column of B, and we write out what the sum is, okay? Next, once you've done all that, right, so your last entry of the first row in the product is A11 B1q plus A12 B2q and so on, up to A1n BnQ. All right, now once you've done the last entry in the product, so first row times last column, and add the result, then you move on to your next row of the product. So you take the second row times the first column, and so that, for example, is A21 times B11 plus A22 times B21, and so on up to A2n times Bn1. Okay, so now that we've got that, we move on to second row of A times second column of B, and you write down what that would be, and so on, right? But what I'm trying to tell you is that there's a little pattern here. So you see, if I just focus on one random entry of the product, what we have is the 1 there matches this 1, the 2 here matches this 2, the n there matches this n, so I can represent this as a sum A2 times, say, some, or k goes next, and then multiplied by bk1, but then I say add them all up over k, so as k goes from 1 to n. And that's what that Greek letter sigma means. It means add all of these up. So this is exactly what we have here, where we say k equals 1, that gives us this, k equals 2 gives us the next entry, k equals 3 would give us the next one after that, and then k equals n is the last one, but that's where we stop. Okay, so that's what this is. Now, but notice the position here, this is the second row, but the first column, we have a 2 and a 1 on the outsides, right? So this is equal to C21, where this is the matrix C, is the product. Okay, so C21 has a formula involving a sum, but actually we could do this with every entry, and so we could say that let's see, Cij equals the sum over k, from k equals 1 up to n, of aik times bkj. Alright, so this describes the generic element of the product. And so I can write that AB is equal to, characterizing that with this sum, and the product is an M by Q matrix. Okay, now that's a lot to take in, right? There's a lot of hieroglyphs here that you might find a little bit overwhelming, right? So this is generically how to multiply two matrices, but let's have a look at example 6.9, where we have a concrete example. Okay, so example 6.9 says the matrix A is equal to 3, 0, 4, 1, 1, minus 1, 0, 2, 3, and the matrix B is equal to 6, 2, 0, 3, 1, 2. Alright, and we want to take the product if it's defined. So calculate AB if it's defined. So what we need to do is work out, okay, how many columns are there in A? there are 3 columns. Does that match the number of rows of B? Well, yes. So AB is defined. So is defined since A has 3 rows, which is equal to number of columns. No, it's the other way around, isn't it? So it has 3 columns. A has 3 columns, which agrees with the number of rows of B. There we go. Okay, so the product is defined. Now let's calculate it. So AB equals, we'll write this out, 304, 11, minus 1, 0, 2, 3. Then we'll put B next to it, 6, 2, 0, 3, 1, 2. Okay, I'm taking this first row and matching it with the first column and doing what is like a dot product of the two, right? So 3 times 6 is 18. Then we have plus 0, then plus 4. Okay, now that we've got that written out, we move on. First row times second column, and we place it here. So 3 times 2 is 6. Then 0 times 3 is 0. 4 times 2 is 8. We add that together. Okay, so we've done the first row with each of the columns. Now we move on to the second row of A and match it with each of the 2 columns. And so we have 1 times 6 is 6. 1 times 0 is 0. Minus 1 times 1 is minus 1. Let's put brackets around these to separate them so we don't get them mixed up. Okay, next, second row of A times second column of B. So for this we've got 1 times 2 is 2, plus 1 times 3 is 3, plus minus 1 times 2 is minus 2. Okay, so we're done with that. So now we move on to the third row and we match this with each of the columns one by one. So 0 times 6 is 0, plus 0 times 2, or 2 times 0 is 0, plus 3 times 1 is 3. And finally, last row, last column gives us 0 times 2 is 0, plus 2 times 3 is 6, plus 3 times 2 is 6. And now we just need to simplify. Okay, so 18 plus 0 plus 4 is 22. 6 and 8 is 14. 6 minus 1 is 5. 2 plus 3 is 5 minus 2 is 3. 0 plus 3 is 3. And 6 and 6 is 12. So we have our product written here. Alright? Now, if I were to do this in summation notation, which would be a pretty bad idea, what would I be doing? Well, in summation notation, I've described the generic entry in summation notation. So, if I were to seek out the entry in the product, the A21 entry, then I would have, say, C21, which would be this 5 incidentally. So that would be the sum of, from k equals 1 up to 3 of, let's see, we would have the that would be the second row times the first column, right? That's right. So it would be 1 by 6 plus 1 by 0 plus minus 1 by 1. Okay, but I don't need this anymore, right? Because I've actually taken that sum now. And so again, I get 5 for that. All right, but this other way of representing it is mostly useful when it comes to symbolic demonstrations that something is true, right? Whereas in practice, you just want to do this process when you just have numbers involved. Okay, so let's move on to the next example or remark or something. So example 6.10 says, let A be 3, 1. So A equals 3, 1, 0, 5. And B is equal to 1, 1, 3, minus 1. So these are two 2 by 2 matrices. Determine whether AB and BA are defined. If so, calculate them. Okay, well, so the product A times B, so AB is equal to 3105 multiplied by 113 minus 1. And so this is, we just take this row, match it with this column, and put that in the first entry. So we've got 3 plus 3. Then we move on this row, match with this column. So we have 3 minus 1. Then this row match with this column is 0 plus 15, which is 5 times 3. And then this row match with the last column of B is 0 minus 5. And so we've got 6, 2, 15, minus 5 as our product. Now the other way around doesn't give us the same thing and may not always be defined, right? But it is defined in this case because they're both 2 by 2 matrices. So we've got 3, 1, 0, 5. Okay, so first row, first column in the first entry of the product. So we've got 3 plus 0. Okay, moving on, first row of B multiplied by second column of A is 1 plus 5. Okay, moving on to the next row of B with the first row of A. So 3 times 3 is 9 plus 0. Then we've got first row, second column of A. So that is 3 minus 5. Okay, now we simplify. So 3, 6, 9, and minus 2. Okay, so you can see these two don't agree. So we don't have AB equal to BA in this case. And in general, these two are not equal, but they could be equal in some special cases. Alright, so I forgot to go back and do the other one the other way. So if you go back to the previous example, now BA, if you were to write this out for this example, you'd be looking at 620312 multiplied by 304 11 minus 1 and 023. However, if you try to match this one with this one, it doesn't work because we've got 2 entries in the first row of B, but 3 entries in the first column of A. So this does not exist. Okay, undefined, D&E does not exist. So we can see that we cannot possibly have AB equal to BA in this case because BA is not even defined for example 6.9. Alright, so let's move on now to example 6.11 that says that there are 3 factories, F1, F2, F3, and 4 products, P1, P2, P3, P4, and 2 suppliers. Which supplier is best for each factory given the data below? Okay, now, this one is best looked at via probably screen sharing. So I'll see whether I can go back to my usual view of my screen. So I'll see if it works just shrinking this down, and then I will have to minimize my screen. So hopefully you can see my screen now. So there are 3 factories. Okay, so we've got our data here represented in I guess we could call this a table, but within that table we could see a matrix 6, 5, 3, 1, 3, 6, 2, 2, 3, 4, 3, 1. And then over here we've got some dollar values. And it says which supplier is best for each factory given the data below. Okay, for example, the table on the left shows that 2 units of product 3 are located at factory 2. So that's this entry right here. 2 units of product 3 located at factory 2. 4 units of product 2 are located at factory 3. Okay, F3, so that's the third row and the second column. That should say P subscript 2 for product 2, right? So you might want to write that over your copy of the notes if you have that printed out. Okay, the table on the right shows how many dollars each supplier is charging for each of the 4 products. Product 2 from supplier 1 is $2 and product 4 from supplier 2 is $17. The question asks whether it's better for a given factory to use supplier 1 or supplier 2 if they must obtain the goods from one supplier. So for factory 1, the sum of the cost from supplier 1 would be, so what we've actually got here is a matrix product, right? So we've got 6 times 1.5 plus 5 times 2.00. So these are dollar amounts times product amounts. So that is the first row of this one multiplied by the first column under S1. Right, so this is a matrix product. Okay, so taking that matrix product, then we have a 50 in the top left entry. Okay, so moving on to the second supplier, that would be multiplied by the second column right here. And so multiplying that out, we get 49. So in our product of the 2 matrices, we've got 50, 49, 58.5, 61, and 43.5, 43.5. So in the product, it shows that factory 1 should use supplier 2, since 50 is greater than 49, or 49 is less than 50, so the costs are less with supplier 2. Factory 2 should use supplier 1 since 58.5 is less than 61, so the costs are lower with supplier 1 for factory 2, and factory 3 could use either supplier 1 or supplier 2 since both of those numbers are the same. Okay, now let's move on to a property of matrix multiplication here. This says matrix multiplication is associative. So this means that for all matrices A, B, and C for which those products within are defined, it doesn't matter whether we calculate BC first or calculate AB first. We can move the position of the brackets so long as we don't change the order of the matrices. Okay, so don't swap the order around, but you can move the brackets according to your choice. Now that is incredibly tedious to verify using an arbitrary M by N and N by Q matrix, but this gives you a reason why to use that setting out that we had earlier with the summation notation, right? So if you had to verify that this is true, this is how you would go about it. You would use the summation notation to do that. Right? Because you can easily characterize the entries in the product of A and B, for example, to be just like this. And then you would take this generic entry and multiply it by a generic entry of C, and you would get a more concise version of this, right? So if you had just the ordinary, let's go back a few pages. Well, it's actually many pages, isn't it? to go to the general product. I thought I saw it here. Okay, maybe it's up here. So if you had something like this and you would multiply it out, well, you'd have a massive mess, right? So it's better to go for the abbreviated form that has summations in it. Alright, moving on. What have we got here? Okay, example 7.11. So let's just have a look at this because this is more repetition of the same. But it introduces the identity matrix. Now the 2 by 2 identity matrix, we call that uppercase I, but it's 1, 0, 0, 1. So we have 1s on the diagonal and 0s on the off diagonal. So what we should learn here is that any matrix for which the product of is defined multiplied by the identity matrix, if the product is defined, then the product of this matrix A times the identity matrix will always return the matrix A. And that's the whole point of the identity matrix. It's like the number 1. When you multiply any number by 1, you get the same number. For example, 8 times 1 gives you 8, the number I started with. Okay, minus 75 times 1 gives minus 75. So the matrix I is analogous to the number 1 in multiplication. And conversely, I times this matrix A returns A. So that's what we have shown here. Have I just jumped into the next section? Possibly so. So let's have a look, because this is suddenly saying 7. Okay, I better stop and go back to theorem 4, because that's the last thing before the next section. Okay, so let A and B be 2 matrices for which the product AB is defined. Okay, determinants are multiplicative, meaning that the determinant of the product of A and B is the product of their determinants. That's a really important result. And it can be used to verify a lot of matrix identities, and it can be used to simplify your own calculations. Alright, I'm going to stop here, and I'll see you in the next video.